Today, we'd like to go through the procedures necessary to calibrate the two basic types of turfgrass fertilizer spreaders. And I'd like to spend a little bit of time explaining the features of each of these spreaders. But before we do that, the question comes up often, why is it important to calibrate these spreaders? Let's think of a couple of reasons, some obvious reasons. Number one is cost. You certainly don't want to apply any more material to a turfgrass area, or any area for that matter, than what's actually needed. All the material that you put out that goes beyond the recommended rates or the rate that you were looking to put out is costing you money. Number two, if there's a misapplication and you apply too much material to the site, you take a chance of having damage to the turf. And a lot of times this is seen as turfgrass fertilizer burn. And that obviously sets turfgrass back and takes some time for that to recover. Number three, we've got to be careful about the chemicals we're introducing into the environment, and we don't want to put any more than what's actually necessary to get the job done. With that, let's examine each of the two types of fertilizer spreaders that we use in a typical turfgrass management program or management system. This is a drop type spreader. It's characterized by, inside the hopper area is an agitator that's connected to the axle. And the principle is, as the wheels turn, the agitator turns, allowing the fertilizer granules to fall through a series of holes or openings on the bottom of the hopper. This is a very good piece of equipment. The thing that you have to remember is that you have a fixed swath. In other words, you're not going to spread the material any wider than the span between the two wheels. The nice thing about a drop type spreader is that they're very, very precise, and the other thing that's extremely positive about this type of equipment is that there's less chance of drift or applying the fertilizer materials to those areas that you don't want the material to go onto. In other words, there's less drift, there's less chance of applying materials to a non-target area. In this regard, we're talking about fertilizers dropping exactly where the fertilizer spreader runs. The disadvantage of such a unit is the small swath. As I said, we have the distance between the wheels of where the fertilizer comes out, but in this case that's only 20 inches. So you can see that on a large area that would take some time to fertilize an entire area. Another thing you must be aware of, they're very prone to, if you don't have proper overlap, it's very prone to skips between each pass through the turfgrass area, which would allow it to, some areas not to be fertilized and not have the full color of the other surrounding areas. Also, sometimes when you try to compensate for that and have it overlapping too much, then we've got dark green stripes where you've overlapped the wheels too much between passes. Let's contrast this drop type spreader to a rotary spreader. This is our other basic type. With the rotary spreader, we usually have a larger hopper to contain the fertilizer, and there's usually a series of holes in the bottom of the hopper ranging from 1 to 3 in this case, in which the fertilizer material will fall through onto this rotating plate or an impeller. Through a series of gears, as the wheels turn, the impeller turns, throwing the fertilizer material out in a semicircular arc in front of the spreader. This is a very good unit, and it's particularly nice in large turfgrass areas. In other words, depending on the material you use, as well as the speed that you're walking, you can have a spreader swath, a delivery swath, up to 15, 20 feet. Whereas, remember, back on the drop type spreader, that may have only been 2 feet. Of course, you can get drop type spreaders in larger units, of course, than just 20 inches. But you can cover a great deal of area here very rapidly. Now, one problem is they're not quite as precise as far as the delivery goes compared to a drop type spreader. And another problem is you do have the potential of applying material to non-target sites. Because of the throw of the material, it's possible to throw it into vegetable gardens or flower gardens or other areas where you just soon not have the material go. So that would be a disadvantage. But the large area and the ease of applying probably compensates for some of those other concerns. Okay, as we go and consider calibrating fertilizer spreaders, what is the basic purpose of doing this exercise? What we have to keep in mind is that what we want to determine when we're going through a calibration process is determining the actual delivery rate of the spreader. The delivery rate, when I use that term, delivery rate, we're talking about the average amount of product or fertilizer material applied over a known area. This is expressed usually in pounds per 1,000 square feet. That's our whole objective here. Now, what's our very first consideration when we start this process? The very first thing you have to think about is, what rate of application am I going to use? Or another way of saying it is, how much nutrients or the nutrients that the plant needs do I want to apply? There's two ways about going deriving the answer to that question. First, you can simply look on the fertilizer bag itself. Now in this case, most companies, as they they sell their products, on the back of the bag, and we always recommend that you read the directions and label carefully, on the back they will give some valuable information. Number one is they tell you just how much area, turf area, this bag will cover. In this case, this particular bag would cover 10,000 square feet. Another thing that they tell you is the spreader setting. And they'll usually list that for a variety of spreaders that are commercially available. Now this is helpful information. However, we know sometimes the spreaders and the settings that they recommend you use are not always as accurate as we would hope they would be. Therefore, we believe it's better to calibrate rather than rely on the information on the bag itself, that you calibrate your own spreader with the material that you plan on using, so that you are absolutely sure of the material that you're going to apply and the rate that you plan on using. What we'd like to do now is begin to go through the actual procedure. And for our purposes today, let's just assume we're going to apply 1 pound of actual nitrogen per 1,000 square feet. And what we're going to use in this exercise is a fertilizer material that has an analysis of AA8. You remember that these three numbers represent the percent of nitrogen, phosphorus, and potassium in this bag. And this is on a weight basis. In other words, in this particular case, for us to apply 1 pound of nitrogen over 1,000 square feet using a material that's 8% nitrogen, we have to apply 12.5 pounds of this material over the 1,000 square foot area. Obviously, if this was 100% nitrogen, then we'd only have to apply 1 pound of this material over that same area. But since we're dealing with such a small percentage, we have to apply more material to give us that equivalent 1 pound rate. As we think about calibrating, and you've made up your mind of how much you want to apply or what number you're shooting for, in this case we're going for the 1 pound rate, needing 12.5 pounds of actual material over a given area. What we have to do is establish a known area in which we can collect our fertilizer material. What we've done over on this side is we've already established with a tarp our known application area in which we're going to collect the fertilizer material. Now, in this case, what we have is a plastic tarp that's 15 feet wide and 20 feet long. Okay? That's only part of the numbers that we need to calculate the area. The other thing we need is we have to determine the width of spread of whatever fertilizer spreader we're using. In other words, we know that it's 20 feet long, but we don't know what the width of this is. Every time you're going to calculate area, you have to multiply length times width. We have the length, but now let's calculate the width. And the way we do that is we put fertilizer material that you're going to use in the hopper and run it across your area and determine how wide of swath the material is being distributed out over. So let's do that right now. It's not real important at this point to have the settings on the spreader at any particular spot, because all we're trying to do is get a feel for how much material or the distribution of this material across the known area. So we'll put in just enough fertilizer material so that we can determine the swath width of this particular fertilizer. Now usually what we do is we want to walk at a constant speed across the area, and you want to open the holes to allow the material to come out just as you're reaching the tarp itself. Okay? I could tell from that pass that we had about a 10-foot swath from this particular spreader with this particular material. That would give us, if we had a 20-foot length and a 10-foot swath, we have 200 square feet of application area. Now, keep in mind, 200 square feet, what we're trying to finally derive is how much material to apply over 1,000 square feet. So this is about 1/5 of the area that we're ultimately looking for. So we are going to need, we wanted 12.5 pounds over the 1,000 square feet, but since we're only dealing with 200 square feet, we want to get about 2.5 pounds of this material spread over that application area where we're going to sweep it up, collect it, and then weigh it, and that will be the equivalent of 1 pound nitrogen per 1,000 square feet, or the total amount of fertilizer of 12.5 pounds per 1,000 square feet. All right, let's begin the actual calibration process. What we want to do now, class, is go ahead and actually run through a first trial run, and you'll see later that sometimes it's going to take 1, 2, 3 times to get the exact setting that we're looking for. When you start handling fertilizer materials and chemicals in general, and you're applying them and putting them in fertilizer or sprayers, it's important to have protective clothing and certainly have gloves. Although these materials are not particularly hazardous, they are salts, and they can be irritating to the skin, depending on the type of material you're working with. What I'd like to do is put a little more fertilizer in the hopper. It's not necessary to fill the hopper to the top. And then I'm going to select the setting. And at this time, if there's something on the bag that you're using to start as a starting point, then do it. Other times, it's just a matter of guess. You guess at it and hope that you're close to what the actual setting will ultimately be. Again, now we're going to do the procedure that we already did to establish the size of our area. But this time when we apply it, we're going to come back, sweep it up, collect it, and weigh it, and see how close we get to that 2.5 pound rate that we're shooting for, which again, remember, that's the equivalent of about 1 pound of nitrogen per 1,000 square feet. Okay, so let's try this. Okay, what we're going to do now is get a broom and start. Sometimes if the wind's not blowing very hard, it's possible to just take the end of the tarp and kind of shift the material down to a corner where you can pick it up, actually drop it into a bucket. But in this case, on a day like today where the wind is blowing, it's probably easier to go ahead, take a broom, and very carefully try to get as much of the material that was applied into a pile. This is 200 square feet. It shouldn't take us that long to bring this material all together, because this is material we're going to weigh. Okay, I've pretty much got the material that was distributed over this area in a pile. And Mike, if you'd come in and give me a hand, I'd like to sweep this up. Go ahead. Go ahead. Okay, class, what we're going to do now is take that material, put it in a bucket to where we can get a weight. And again, we're shooting for, how close did we get to 2.5 pounds over this 200 square foot area? Let's go on over to the scale. Okay, class, what we usually do when we're going to weigh material like this is a scale that was easily purchased at a discount store, what have you. And a lot of times it's necessary, we weigh the bucket beforehand so that the scale is zeroed back to a starting point or back to zero, so that when we add the material, we don't have to calculate out the weight of the bucket. Okay, so it looks like we've got that right on. It's at zero. Now if we add the material, I can see that we're up to about 3 pounds of material. We were shooting for 2.5 pounds of material, and but what we don't know until we make the calculation, the air calculation, we don't know if that's within the range that's acceptable. Now, looking at the formula that we're going to use to determine the air, we can easily see that 3 pounds spread over that amount of area when we're shooting for actually 2.5 pounds is that we have exceeded the 5% air limit. In fact, I think this is exactly 20% air, and that's too much. In other words, what we have to do is go back and do the process again. This time what we'll do is turn the setting down, close those holes a little bit more so less material comes out. Hopefully then we'll be at about that 2.5 pound rate or somewhere within that 5% air limit. Okay, so let's go through the process again. Okay, as we've just seen, we're a little bit over our desired rate. In fact, we exceeded that 5% quite a bit. So what we want to do is set the setting down just a little bit to try to get the delivery rate at about that 2.5 pound level. And there's an adjustment on the back of spreaders that it controls the size of the openings beneath the hopper. Okay, let's try it now. I've set it down, and let's see if we're any closer. Okay, let's check out the weight this time. Over our second run, where we adjusted the spreader down just a little bit to see if we can't get closer to that 2.5 pound weight that we're looking for. Okay, in this case, it looks like we're just about there. According to this scale, it's about 2.6 pounds, and that would be the equivalent of about 13 pounds of fertilizer material over 1,000 square feet. Now, if we do our calculation for the air, remember, we've got to stay under that 5% or less. That works out to be about a 4% air. So we're within the range that we need to be, and the setting that we have on the spreader at this point is what we would use when we're actually applying that material over the turfgrass area. Be sure to write down that marking or the setting of the spreader somewhere so that you can refer back to it later. The next part of this exercise is how do you go about calibrating a drop-type spreader? It's basically the same procedures. Now, there's one major difference is that the area, your application area that we determined before, is going to be different than what we did for the rotary spreader. Let me show you why that's going to be. With a drop type spreader, as I discussed with you earlier, here's our application width right here. We cannot exceed that. So when we had 10 feet with the rotary spreader, we have essentially 20 inches from wheel to wheel here. So now what we do is we're going to multiply our 20 inches of our spreader width times the length of the tarp, which is 20 feet. And after you make that calculation, you'll see our square footage is 33 square feet. That's our application area. That's down considerably from the 200 square feet we got with the rotary type spreader. After you determine your application area, then it's a matter of going through the same procedures we already have gone through for the rotary spreader. But let's go ahead and just see how this works, and you'll see that there is some differences. Because we're applying to a smaller area, we are not going to collect as much material. Again, let's begin by making sure the openings are closed, and we start at some setting that sometimes can be right on the bag as a good starting point. But remember, just because the bag says it's going to be setting 3, 4, 5 on a Scott spreader or whatever spreader you may be using, doesn't mean that's the way it will work out. There could be variation there, but it's a good place to start. Take the fertilizer material. You don't have to fill the hopper up. We just need a little, maybe a third of the hopper actually full. Make sure the agitator and holes are completely covered. And then walk the area the same pace as you would if you're applying the material to the turfgrass area, and we'll see how we come out. Okay, class, we went ahead and we ran it through, and now over a 33 square foot area that we calculated, we're shooting for a 0.41 rate. And let's see what we've collected now. This looks like it's just over half a pound. It's 0.6. Well, that's over our intended application rate. That actually figures out to about 18 pounds of fertilizer material per 1,000 square feet. That definitely will exceed our 5% error term. If you do the calculation for the error, that comes out to a whopping 44% error. That's totally unacceptable, so we're going to have to go through the procedure one more time. This time set the spreader down, the setting a little bit lower, and hopefully we can come up with that 0.41 rate or weight that will be the equivalent to the 12.5 pounds over the 1,000 square feet. Okay. Let's try it. Now remember, what we have to do is turn it down just slightly. It's only a little bit. And I've mentioned before that sometimes this may take 2, 3, 4 times. But that's okay. It's important that we get it right and get it right on the weight we're looking for. So let's try it and see how we come out this time. Well, let's see how this compares to the weight that we're looking for. Remember, the 0.41, just a little bit over 0.4. It looks like we did real good this time. It's at 0.43. That's much closer. And if you make the calculation, now that's going to be about 13 pounds of material over 1,000 square feet. Remember, we're shooting for 12.5 pounds. And if we do the error calculation, put the formula up, and you'll see that that's about a 4.8 error, which is under our 5%. So this is fine. The setting that we've just come up with is good for that spreader for this material. Let's go ahead at this point then and show you one other method that's not quite as precise as the one that we're using here, using the tarp and sweeping it up, but it works quite effectively. And it can be used for either drop type or rotary type spreaders. Now the procedure used here is, the first thing you have to do is measure off a large area. And in this case what we did is we measured off 50 feet. And we've got two stakes that I'm going to walk the spreader across, and I'm going to go down and then I'm going to come back for 100 linear feet. We remembered that the width of our spreader, of our rotary spreader, was 10 feet. So if I push this rotary spreader up and back between our measured 50-foot area, I'm going to have 1,000 square feet. How we calculate, or how we actually calibrate the spreader is, we're going to mark on the hopper, inside the hopper, the level of the fertilizer inside the hopper, and we're going to mark that right on the hopper. We will push, so now we know how much fertilizer was in the hopper when we started. We're going to push the fertilizer spreader over the area, come back, see how much lower the fertilizer is than the mark, add a predetermined or pre-weighed amount of fertilizer to the hopper to bring it back up to the mark. Then we'll know exactly how much material we put out over the 1,000 square feet. Okay, let's try it. Okay, class, what we've done then is we've covered our 1,000 square feet application area, and it's very obvious that we applied a good amount of material because it's a few inches below the markings on the hopper. Now what I did earlier was weighed out a known amount of fertilizer in this bucket, and it's right at 15 pounds. I'm going to take the material over to the hopper and bring the level back up to the marks. Smooth it around and get it nice and level back up to the marks that were made on the hopper. And now I'll weigh the remaining material, and then I'll see exactly what my application rate was. Okay, it looks like I'm about 2 pounds of material left in the bucket. In this case, we applied, of the 15 pounds that we had, we applied 13 pounds over a 1,000 square foot area, because right here we have 2 pounds remaining in the bucket. If you make the calculation, remember what we want to apply over 1,000 square feet is 12.5 pounds. We applied 13. That's very good, very lucky. Usually, as we've already found out today, it may take us 2-3 times to do that exercise. But in this particular case, it came right on, and that would be the setting we would use for this particular fertilizer material. Class, we've covered 2 methods of fertilizer calibration today. Both methods are good. The TARP method's a little more precise. Using the walking method between the known area is quicker and very effective, and it works for both the drop-in rotary type spreaders. Either one will do you quite well. What we'd like to do the remainder of this lesson is watch a video by Spraying Systems Company, which they've allowed us to use, which they demonstrate the proper procedures used in calibrating a boom type and a backpack type sprayer. So stay tuned, and we'll talk to you later.
Calibrating turf grass sprayers. Calibration. No matter what type of turf spraying that you do, whether it's using a boom, boomless spraying, or spray gun applications, you must calibrate accurately to obtain effective pest control. In the next few minutes, we will address the variables important in the calibration process, and then go through some step-by-step examples for boom spraying, boomless applications, and handgun spraying applications. How important is calibration? Calibrating your sprayer can minimize risks to the environment caused by chemicals that may have been over-applied. Calibrating your sprayer can also save money, either in chemical costs from over-application or the cost of a rescue treatment because the correct amount of chemical was not applied during the first application. One study performed at the University of Nebraska found that out of 53 private and municipal golf course applicators, 83% misapplied their chemicals by plus or minus 5%. The average cost of this misapplication was over $25 per acre. These figures did not include possible damage to the turf. In understanding how to calibrate a sprayer, you must consider three main variables. They are 1. Nozzle flow rate, 2. Ground speed of the sprayer, and 3. Nozzle spacing or swath width. These variables determine how much chemical you are going to apply. Nozzle flow rate. Simply stated, the amount of liquid sprayed from the nozzle in a given amount of time. Nozzle flow rate is affected by three variables. They are A. Orifice design, B. Spray pressure, and C. Specific gravity. Each nozzle type, whether it's a flat fan, hollow cone, or full cone, has a different orifice design. Various nozzle types all perform differently while spraying due to internal design characteristics. For example, a flat fan tip and a hollow cone tip spraying the same flow rate at one pressure may not be applying the same rate when the pressure is increased. Therefore, consult the manufacturer's catalog to ensure that you are getting the proper nozzle flow rate. Pressure. Nozzle flow rate varies with pressure. The higher the pressure, the greater the flow rate. With flat fan nozzles, the flow rate varies with the square root of pressure. Therefore, you must increase the pressure 4 times in order to double the flow rate. For example, a nozzle spraying at 10 psi will deliver twice the amount of liquid if the pressure is increased to 40 psi. Specific gravity. Spraying solutions other than water, such as liquid fertilizer, may affect nozzle flow rate because the specific gravity of the fertilizer is greater than that of water. For example, an applicator will apply 10% less chemical if he is using a carrier at the rate of 10.65 pounds per gallon instead of using water as a carrier. Most nozzle manufacturers' catalogs contain conversion tables, such as this one, to help you in choosing the correct size nozzle. The second calibration variable to be considered is the ground speed of the sprayer. An error of only 1 mile per hour can affect your application rate by as much as 1/2 gallon per 1,000 square feet. Doubling the ground speed reduces the gallons of spray applied by 1/2. For example, a sprayer applying 2 gallons per 1,000 square feet traveling 3 miles per hour will apply only 1 gallon per 1,000 square feet or half as much when traveling at 6 miles per hour. The third variable is spacing. This would be your nozzle spacing in boom spraying or your effective swath width in boomless and handgun applications. We will discuss effective swath width later in the program. Doubling the nozzle spacing or swath width will decrease the gallons per 1,000 square feet sprayed by 1/2. For example, if you are applying 2 gallons per 1,000 square feet on 10-inch centers, you will only be applying 1/2 that rate, or 1 gallon per 1,000 square feet, if you increase the nozzle spacing to 20-inch centers with the same type nozzles. Now, Before going through the actual calibration process, you should perform a check throughout your entire system. Check for worn or split hoses, clogged or cracked strainers, and leaky valves. Check parts thoroughly. Nothing is worse than having a leak in the system after chemical has been added to the tank. Now, let's go through the actual calibration process with some simple steps for you to follow. Step 1 involves sprayer speed. Knowing your sprayer speed is essential. Not all speedometers are correct. Wheel slippage, tire inflation, and various turf conditions are all factors that may affect sprayer speed. Determine your actual sprayer speed driving on turf with the tank half full of water, so that you can be as accurate as possible. Check the time required to travel over a 200-foot test course. Trees, yardage markers, or flags can be used to mark the course. A stopwatch or calibration calculator can be used in determining the time to travel the length of the test course. After determining travel time, use this formula to determine speed in miles per hour. As you can see, speed in miles per hour equals the distance traveled, measured in feet, times 60, which is a constant. This divided by the time it took to travel the test course, measured in seconds, times 88, another constant. For example, if it takes you 34 seconds to travel a 200-foot test course, using the equation, you would find that you were traveling 4 miles per hour. The T-Jet calibration calculator does this calculation automatically. Also, many nozzle manufacturers' catalogs contain tables for quick determination of speed. Step 2 involves inputting the known variables. The nozzle type. There is a different nozzle type for each particular application, whether it is insecticides, herbicides, or fungicides that you are spraying. The recommended application volume for the pesticide. This can be found on the manufacturer's chemical label. Measured sprayer speed. This was determined earlier by traveling over a test course. Nozzle spacing. This is simply the number of inches between each nozzle on the boom while broadcast spraying, or your effective swath width in inches for boomless applications. While you are going through the actual calibration process, write these figures down so that you can refer back to them later. Step 3 involves calculating the proper flow rate for each nozzle on the boom. When calculating in gallons per 1,000 square feet, use this equation. Gallons per minute equals gallons per 1,000 square feet times miles per hour times nozzle spacing, W in inches, divided by 136, a constant. When calculating in gallons per acre, use this equation. Gallons per minute equals gallons per acre times miles per hour times nozzle spacing, W in inches, divided by 5940, a constant. The two equations just mentioned can be found in most nozzle manufacturers' catalogs and can be used to find any one of 4 variables if the other 3 are known. Here is an example with the variables shown in the gallon per 1,000 square feet equation. If an applicator wants to broadcast 1 gallon per 1,000 square feet, travel 4 miles per hour, and have 20-inch nozzle spacing on the boom, he would need a nozzle that would spray 0.59 gallons per minute. This figure should then be compared with a manufacturer's catalog to choose the correct nozzle size with regard to flow rate. Step 4 involves correcting nozzle pressure. Don't assume the pressure at the nozzle is the same as the pressure upstream in the system. Pressure is lost through hoses, valves, and other parts of the system. Make sure you know the pressure at the nozzle and compare it with the gauge on or near the sprayer controls. The pressure reading at the sprayer controls may be very different from that given at the nozzle, thus allowing for error in the flow rate from the nozzle. Consult the manufacturer's catalog to find the approximate pressure needed to get the proper flow rate from the nozzle. Next, collect and measure the volume of spray from a new nozzle. A new nozzle minimizes errors that may occur by using older and sometimes worn or defective nozzles. Set the pressure and collect the flow from the new nozzle. Now fine-tune the pressure either electronically or manually until the proper flow rate found in the manufacturer's catalog is collected. Step 5. Checking your system. Check the flow rate of the old nozzles on each boom section. If the flow rate of any tip is 10% greater or less than that of the newly installed spray tip, recheck the output of that tip. If only one tip is faulty, replace it with a new tip and strainer. However, if a second tip is defective, replace all tips on the entire boom. This may sound unrealistic, but 2 worn tips on a boom are ample indication of tip wear problems. Replacing only a couple of worn tips invites potentially serious application problems. Run through the calibration process throughout the season. Don't just check your sprayer at the beginning and assume that you are still applying the same rate throughout the season. Some types of nozzles can wear easily, or other variables may change slightly, all contributing to the chance for misapplication. Boomless applications. While calibrating for boomless applications, the operator must consider his effective swath width rather than nozzle spacing on the boom. The effective swath width is the area from the center of one drive row to the center of the next. For example, if an applicator is using a boomless nozzle which produces a swath width of 60 feet and is overlapping his spray 100%, his effective swath width would be 30 feet. As stated earlier, W in the equation would simply be the effective swath width in inches. Let's go through an example. An applicator needs to apply 1/2 gallon per 1,000 square feet while traveling 4 miles per hour and effectively covering a swath width of 30 feet. To calculate gallons per minute needed from the nozzle, first multiply 30 feet times 12 to convert feet to inches. Then take that number, 360, along with the other variables and enter them into the formula. Gallons per minute equals 1/2 gallon per 1,000 square feet times 4 miles per hour times the effective swath width, 360 inches, divided by 136, a constant. In this example, the nozzle should produce 5.3 gallons per minute water. Next, collect the flow rate of the nozzle by directing the flow into a collection device and then weigh the water. For example, an applicator collects 44.3 pounds of water in 1 minute. A gallon of water is equal to 8.34 pounds. So you would divide 44.3 by 8.34 and get 5.3 gallons per minute. Spray gun applications. Calibration procedures for spray gun applications are different from those methods involved with mechanized sprayers. Let's go through the spray gun calibration process with some simple steps for you to follow. Step 1, walking speed. Determining one's walking speed is achieved in the same manner as with motorized equipment. An applicator can use the following equation to determine his walking speed. Multiply the distance traveled in feet by 60 and divide that number by the time in seconds taken to travel that distance multiplied by 88. This equation will give walking speed in miles per hour. Step 2, input known variables. The basic equation that is used in spray gun applications is shown here. Gallons per 1,000 square feet equals coverage time multiplied by flow rate from the nozzle. For example, an applicator wants to apply 3 gallons per 1,000 square feet using an overlapping spraying method. He has determined that he can spray 1,000 square feet in 40 seconds. Step 3, calculating. Input the variables in the equation. As you can see, coverage time, 40 seconds per 1,000 square feet, multiplied by the variable gallons per minute, equals the desired application rate of 3 gallons per 1,000 square feet. In order to find gallons per minute needed, the applicator would multiply 3 gallons per 1,000 square feet by 60 seconds. Next, dividing 180 by the coverage time, 40 seconds for 1,000 square feet would show the applicator would need 4.5 gallons per minute from the nozzle on the spray gun. So, from now on, it's up to you. Don't forget, calibration helps ensure accuracy to maximize the chemical's effectiveness. Money is saved by avoiding chemical costs due to misapplication, and calibrating helps minimize risks to the environment from over-application. Talk it over with your friends. Chemical application is a very precise business, and calibrating your sprayer is essential when applying today's turf chemicals.